Okay, going on to topic 3. We are going to multiply radical expressions. And we use a little bit of factoring. And we're going to do some simplifying as well. So a little quick review of the vocabulary. Index number, that in that little niche there on the side of the radical sign. That's where we put the index number right there. Multiples, radicants, and square. Let's get this filled in. Okay, the products of two n-roots is the n-root of the product of two radicants. So here, if the n-root is squared, and this is squared, then the product, you just multiply the radicants and keep the same index number and just the product of those two radicants, 6. We'll have many examples of this. And again, in order to do this, the index numbers must be the same. If no index number is written, it's a 2 there, or the word square. Now, to simplify the n-root, identify factors in the radicand with the exponents that are multiples of the n. So, for instance, the index number is 3, this is 6, and the rule is take away the radical sign, put the index number as the denominator of the exponent that is there, and then just simplify. Now, we did mention that technique in section 1 and in section 2, and we'll be reviewing it here as well. As we go on here, and we want to be on the right page, let's just review what we went over. Index numbers are the same, so we just multiply the radicants. Put it under the radical sign, it'll just be the product. Index numbers are the same. 3 times 5 is 15. X to the third. Index numbers are the same, but notice here these are conjugates. And when we multiply conjugates, they produce the difference of perfect squares. Now in number 8, a little tricky, so let's go over it. I don't know if you recognize this, but if we factor that factors, since this is a perfect square trinomial, into a minus 3, the quantity squared, which is what we have there. So here we have 2 of them, and here we have 2 of them. So we're now going to end up with the 5th root, because our index numbers are the same. And I did forget to put the 5 up there, sorry about that, of a minus 3, and there's a 2 and a 2, so this goes to the 4th. And here it's just all of this under one radical sign. XU YV. And I think that's good. So again, the same index number. So we just multiply, and in a sense this is in a parenthesis because of the grouping symbol, the division bar. So this becomes 3x minus 15. And this becomes 7x plus 14. Now, for these, I want to really stress the strategy we should use. Now, we want to simplify by factoring. Now, this is not a perfect square, so in a sense, this is irrational, and we're wondering if we could do something with it. So the strategy is to put two radical signs, and what we want to do is divide this up into a factor that we'll put here of 200 that is the largest perfect square factor of 200. Now, what are the factors of 200? Well, starting easy, we go 100 times 2. Now, 100 is a perfect square. We take the square root of 100, which is 10, and the square root of 2. So if you can remember this, the square root of 200 is always 10, the square root of 2. So looking at number 12, our strategy, two radical signs. Is there a perfect square factor of 63? And I'm getting ahead of myself. Yes, 9 times 7. You take the square root of 9, which is 3, the square root of 7. By the way, that's what the square root of 63 will always become now. Now here we're getting to the third root, so we'll go to the third root, two radical signs. Now as we look at 27, 27 is a perfect cube, so we'll put that there. Now as we look at x to the 6th, is it a multiple of 3? Yes, so that's a perfect cube as well. And then we have y to the 2nd. That's not a perfect cube, so we put that in the other radical sign. Now since this is a perfect cube, we take it, and this will be 3x. Remember, we're going to divide the 6 by 3 and get 2. And then what's left is the cube root of y squared. And that is the strategy. Divide it into two parts, those parts that are perfect, whatever you want to get, and whatever's left. Okay, now we know the sign's going to be negative, so we put the negative there. And then our radical signs. Now we look at 24. Does 24 contain a perfect cube as a factor of 24? Yes, 8. What's left? A 3. Now, x to the 12th is a multiple of 3, so that is a perfect cube. So we've divided this radicand now into two factors, one being a perfect cube. So a negative goes there. Cube root of 8 is 2. 12 divided by 3 is 4. The cube root of 3. Okay, now here they're giving us in fact function notation, but the same pattern follows. Two radical signs. Is there a perfect cube factor of 40? And here you have to mentally go through them. Well, 8 times 5 is 40, and 8 is a perfect cube. Now, of x to the 5th, what would be the perfect cube there? Well, x to the 3rd. And what's left over? X to the 2nd. And again, what I'm trying to show you here is a strategy for doing them. So we take the cube root of this and get 2x, and then this part just goes like so. Now the tedious part of this will be, of course, putting all these signs into MATLAB, but that's part of what you're doing. So here, remember, it's function. Now as I look at this, I notice I could factor out a 3 out of each term. And then in the other one, I'm left with x squared minus 4x plus 4. Now this is a perfect square trinomial which will factor into x minus 2, the quantity squared. So I'm going to switch these around because I can actually factor this part here. Keep in mind that's under a radical sign. And when I take the square root of that, there's a 2 there, a 2 there, and I'll put it over to the side here. This is what we have, and then there's the square root of 3. Now, the rule is if you take away the radical sign and take this index number and place it as the denominator of that exponent, 2 divided by 2 is 1. So this is going to just become the radicand over here, and you get x minus 2, the square root of 3. And theoretically, I guess you should put that into a parenthesis, because it's not just negative 2 times this, it's this times that. Okay. So following that same protocol here, I've made 2 sets of radical signs, and under the first we're going to put perfect squared factors. X to the 4th, and an x here left over, and then y to the 10th. And we'll get back to those. Now here we're going to have a to the 6th, b to the 6th, and I have a b left over, and c to the 12th. Again, I'm looking for multiples of 3, and then I'm left with c to the 2nd. And then here, remember, we could have a negative there, that's fine, because it's an odd root. And I happen to know that 32 is a perfect 5th power times 10. Then c to the 5th, c to the 3rd. I'm looking for multiples of 5. And then d to the 15th, and I'm left with d to the 2nd. Okay, now you'll note that under these first radical signs, these are all perfect whatever I'm looking for. So this becomes x to the 2nd, y to the 5th. Remember, I'm just taking that index number, removing the radical sign, and dividing that 4 by 2, the 10 by 2, and I get the square root of x. And here this will be a to the 2nd, b to the 2nd, c to the 4th, and then the third root of bc squared. Again, if you have a protocol, a strategy for doing them, they're a lot easier. And then here, this is going to be 5th root of 32. A negative 32 is a negative 2. C, D, remember I'm dividing that by 5, and I get a 3. Then I'm left with this. Now, what I see sometimes, students will get part of this, and then over here, there was actually some fifths left in there. So there shouldn't be any fifth powers left in this second radical expression. I worked on these a little bit to save time, but our strategy, 2 radical signs, same index number. We're looking for a factor of 32, that's a perfect fourth, which happens to be 16. 16 times 2. Now x to the 3rd is not a perfect fourth, so I moved it over here. Y to the 20th is a perfect fourth, so that stays there. Z to the 8th, multiple of 4, and I have z to the 3rd. So now this is a perfect fourth root, and I'm going to get 2 y to the 5th, just dividing that by 4, z to the 2nd, and then this is what's left. Now notice in this second radical sign there are no perfect fourths. That's what we did here. We took all the perfect fourths out and separated that. Now for number 21, you might say, well, multiply these two together. Well, that would make it a number you may not even recognize. But notice what I did. I took 14 and multiplied it 7 times 2. And 21, 7 times 3. Then I reposition the 7s so they'd be under one radical sign. And then 2 times 3 is 6. So this is actually 49 times 6. And the square root of this will just be the radicand 7, the square root of 6. And again, I'm trying to show you a strategy for doing it. Now here we see a 5. And we have 25, which is 5 times 5. So this would become the third root of 5 to the 3rd. Take away the radical sign, divide the 3 by the 3, gives you 1. So this is a 5. Now that's one way of looking at it. You could have multiplied that and gotten the third root of 125, which is 5. Either way. But this is sort of teasing it apart for you to see what's going on. As we do number 23, notice our radicands are exactly the same. So in a sense, it's the radicand squared. Well, since this is the second root that we don't write, and if we take away the radical sign, this becomes that over that which is 1, our answer just becomes 28 x to the 5th. Or, if you can remember, when you see something like this, it's just going to be one of them, because this is this squared. Take the 2 from the index number, divide it, and it just becomes the radicand. We'll be dealing with that in the next section a little bit. Now, for something like this, what would be a strategy? Well, I would suggest that you, since they're the same index number, multiply the 4 times 6 and get 24. And then a to the 2nd, a to the 5th, a to the 7th. And then working from there. Now there's another way to do it too. But again, how many ways do you want to know? And I don't want to confuse anyone. But now we see we have 24. Does that have a perfect cube factor? Yes, we did these before, 8. And then a to the 7th, what's the multiple of 3 here? Well, a to the 6th. And then what's left over is there. So this is going to become 2a squared, the cube root of 3a. And again, we're trying to show you a strategy for doing it. And the same here. I put them all under, and now let's see. We have c to the 3rd with c squared left over, and we have d to the 9th, again multiples of 3, and a d left over. So this then becomes c d to the 3rd, and then the 3rd root of c squared d. Okay, I'll do this in 2 parts. So here we have this to the 4th, this to the 8th. So I'm going to put it under one radical sign as this to the 12th, which is a multiple of 3. So divide that by 3 and we get this as an answer. Now for number 27, as we look at it, we got a 50 here and a 75. So what I did over here, I went to prime factors. And for 75, prime factors. Now notice I have 1, 2, 3, 4. I have 5 to the 4th with these 4 5s. And then I have a 2 times 3. I guess I had that one wrong there. I kept thinking I had a 2 times 2. It's 2 times 3. This is going to be a 6. There you go. Then I had x to the 5th, x to the 2nd gave me x to the 7th. Y to the 3rd, y to the 1st gave me y to the 4th. So now I'm going to use that technique. So this is a perfect 4th. And then I have x to the, and I have to put the 6 over here, x to the 4th, x to the 3rd left over, because this and this make that, and this is a perfect 4th here. So now I take the 4th root of that, which will give me a 5, x, y, and then I have the 4th root of all that did pass the test. A little bit of humor there. Okay, and we'll do the last one. So r to the 2nd, r to the 9th gives me r to the 11th. And then 4 and 6 gives me this to the 10th. So I'm going to use that technique, 2 radical signs. R to the 10th is a perfect 5th power, divisible, multiples of 5. I have an r left over. And then this one happens to be a nice even one here. So when I do this, this becomes r to the second times s plus t to the second, and then the fifth root of r. Well, hopefully again, this will be helpful in developing a system, a strategy for doing it. And you might also, if you haven't watched my whiteboard presentation on this, here it's a little more thorough, but the other is interesting as well.